Let's now consider quantitative solutions for the for those discrete bound state energies. Now, to do this quantitatively, we need some kind of a condition. And the purpose of the animation is to really reveal what the mathematical condition is. So the condition is clearly that we have to must avoid any of those exponentially growing terms in region 3, right? So we have to avoid any term that comes in our solution of the form e to the alpha x minus a with the positive sign in, of course, region 3. Now, if we look at our solution for region 3, which is all the way back up here, here it is, right? We have two exponential type solutions. We have hyperbolic cosine and hyperbolic sine. So the name of the game is going to be to write these in terms of the growing and decaying exponential parts, and then pick off so that we have zero prefactor on the growing exponential. So let's consider how that is going to look. So the approach then, that's the condition. So our approach is going to be to say, okay, so I recall the definition of my hyperbolic functions. Hyperbolic cosine of a value, you will recall, is the sum of the positive and negative exponentials of that value over 2, whereas the hyperbolic sine of the angle is the difference between the positive and the negative exponentials, then divided by 2. And so we are going to substitute these into the expression for phi 3 above, and then we will pick out the prefactor on the growing exponential parts, and we can set that to 0. So we then will have a mathematical condition, right? That is the prefactor, so the e to the x minus a prefactor must be 0, and that prefactor will have the following form. For both the substitution of the hyperbolic cosine and sine, notice both of these terms will both give us factors of 1/2. So I'm going to factor out 1/2 from that overall prefactor. The cosine term then will give me a positive term of plus 1/2 times a growing exponential. The remainder of that term then are these prefactors. So down below I already factored out the 1/2. I now need to copy down this prefactor, which was cosine 2ka. So I have cosine of 2ka plus then it was alpha over k times sine of 2ka. And that then will pick off all of the contributions, the prefactor on all the contributions to the positive exponential from the hyperbolic cosine term. When I turn to the hyperbolic sine term, it also has a factor of plus 1/2, which I've already factored out, times a growing exponential. And the remaining factors on the growing exponential then are the prefactors that we see on the hyperbolic sine, which has a minus k over alpha times sine. So there'll be minus k over alpha times sine of 2ka, and it also has plus cosine of 2ka. Very good. So this then is the key strategic piece of algebra we had to come up with. From this point onward now, it's going to be a method for solving this trigonometric equation. So let's put our thinking caps on and think about this a little bit. We need to simplify this somewhat so we can start to pull out solutions. And one of the things clearly we could think about in simplifying it is to use our double angle formulas. Now these double angle formulas will then give me cosine squared of Ka minus sine squared Ka coming from this term. I will also have, from these two terms, I will have twice sine Ka times cosine Ka. And then finally, this term, much like the cosine, will give me a cosine squared Ka minus a sine squared Ka. So if you think about it, what we have is a second order, right? It's second order because I have like cosine squared and sine times cosine. I have what is known as a second order trigonometric polynomial. And the basic way to solve those then, as we know how to solve any type of quadratic equation in this class, it's going to be some kind of completing the square or some kind of polynomial factorization. So let's get it into that trigonometric polynomial form, and then let's see if we can factorize it. So let's begin with the cosine terms. So there are two of them, but there's a nice convenient 1/2 out in front. So in fact, all I'm left with then is cosine of 2ka, which we know from our trig identity is cosine squared of ka minus sine squared of ka. Now I will come back to the minus sine squared because I want to organize this like a typical polynomial. So that's the cosine squared part. These sine terms, right, both of those terms actually include a factor of 2 and then sine times cosine. The 2's again cancel conveniently against this 2. So I will just have then, say, the first term, alpha over k. And what's left of my sine 2ka then is a cosine of ka multiplying then a sine of ka. So that looks very nice, like a piece of a polynomial in cosine and sine. My next term is minus k over alpha, and it has exactly the same form as before. So there will be a cosine ka times a sine of ka. And now finally, this cosine I had already combined with this one, but I'd written down the cosine squared part. I had better remember to put down the sine squared part. So it's minus sine squared ka. Beautiful. Now I have a nice trigonometric quadratic polynomial. I can now try to factor this as one of the best ways to find the zeros. So to help simplify things. So if we want to factor it, it looks like it's some kind of cosine plus sine type function. So there's going to be a cosine of ka plus some amount of sine ka, which I will determine momentarily. And that is multiplying again some kind of cosine ka with some amount of sine of ka. And now we can check. We can multiply this through and adjust factors as needed to see if we can factor this. Well, cosine times cosine gives me my cosine squared, so I've taken care of that term right away. The next type of term that I would like to see is some kind of alpha over k cosine times sine. So it really feels like this cosine can multiply this sine plus alpha over k. And if I were to do that, then I'd get cosine sine alpha over k. That is exactly this term. Next, I need to generate a minus k over alpha times sine times cosine. But that looks like I could do that because I could take this cosine and arrange it to multiply a sine with a factor of minus k over alpha. And then that will give me my minus k over alpha sine cosine. So that takes care of this term. And now finally, these two are the last of my quadratic terms. I get minus sine squared, and beautifully the k cancels the k, the alpha cancels the alpha, and indeed I've reproduced exactly my above polynomial. And this is very exciting now because you can see I really have two classes of solution, right? I can have either this first term, term 1, right? I have one class of solution where this term gives me 0, and I have a second class of solution, right? One or the other, or technically sometimes both, but these two actually won't ever be 0 at the same time. Either we have a type 1 solution where this term is 0, or there's the type 2 type solution that happens when this term is 0. So it seems like the universe here is trying to teach us something because this factored so nicely and beautifully. I'd really like to know what is it that's so special about these type 1 and type 2 solutions. But in the meanwhile, we can begin to now write down a procedure we need to follow to actually find the allowed energies. So we can focus on these one at a time. So suppose we're looking for a class 1 type solution. So that would be, okay, type 1 solutions would follow the following form. I can actually solve this now for k over alpha. So that gives me a k over alpha equals, And then when I move this to the other side of the equation, to get k over alpha, I then divide by sine. So I have cosine over sine, and that is very famously the cotangent function. So that would be cotangent of Ka. Now, that's one equation that I could solve, but notice it's one equation in two unknowns. I don't know what alpha is yet, right? So if I'm going to boil this down to one equation in one unknown, I had better re-express alpha in terms of k. Now, alpha, you will recall, is actually directly related to k. We had this nice mnemonic to remember it by, and it's simply a Pythagorean theorem, right? Q naught is just a constant, so that's basically given to us at the start of the problem. And I can solve then for alpha in terms of the givens in the problem, Q naught and k. Alpha would just be the square root then of Q naught squared minus k squared. So then this would have the value of k over square root of Q naught squared minus k squared. So really, I'm equating this term with the cotangent. And that then is just one equation and one unknown. I should be able to solve that system. And we will come back to in a moment how we would solve that system. Once I solve it, notice that gives me k. That doesn't necessarily tell me what the energy is. But once I have k, it's a very short hop, skip, and a jump in order to actually find the energy. Because to get the energy from k, I have this handy relationship. So if I square both sides, k squared, move the constants over, h bar squared on top times k squared over 2m, that would give me my energy. So once I manage to solve this simultaneous equation, then the energy then can come out very nicely as just h bar squared times whatever I find for k divided by twice the mass. So that's the type 1 equation we would have to solve. Type 2 is very similar. Now for type 2, I'm dealing with this factor being 0. And so that we can leverage a lot of the work that we've done here. Let's solve this one also for k over alpha. So for type 2, k over alpha will have a different trig function. And to solve for that, I would put this cosine on the other side of the equation where it will come in with a minus sign. Then I have to move alpha over k to that side, which means I'm going to be dividing by cosine. So I will find then that k over alpha is actually sine over, has a minus sign, remember, because when I put the cosine over here, I generate a minus sign. That will become minus the tangent then of k times a. And the rest of the solution then follows the same form as type 1, right? Because then k over alpha I'm actually going to represent with this factor. So I have that simultaneous equation must hold. And then once I solve it, that will give me the value for k. And then to get that value for k, once I have it, I can simply square it, multiply by h squared on 2m, and then voila, I will have my allowed energies. So this then represents the form into which we've simplified the task of finding the allowed states. The next task then is to learn how to solve these types of equations.